One of the surprising findings from the James Webb Space Telescope is just how big galaxies got in the early universe, and not just galaxies, but supermassive black holes. It was expected that you would see these small dwarf galaxies coming together, and we would be on the road to the formation of the much larger supermassive black holes that we see today. But no, astronomers see supermassive black holes with tens of millions, hundreds of millions of times the mass of the sun within the first billion years of the age of the universe. And that leads to a question: how did they get so big so early? And there are the standard model, the light seed model, where small black holes form, they find each other, they pull in gas and dust, and you can get to the sizes that we see, but it's tricky. The heavy seed model, where you get a direct collapse supermassive black hole, that there's enough gas and dust in a region and some way to overcome limits that you just get a gigantic black hole forming all at once. And this has been theorized, and now astronomers think they've found an example of where this is happening. My guest today is Dr. Pieter van Dokkum. He is the Sol Goldman Family Professor of Astronomy and a Professor of Physics at Yale University. Pieter and his team worked with James Webb and found a really fascinating galaxy that's called the Infinity Galaxy. And you see these two galaxy rings shortly or during the collision. Both have supermassive black holes, and yet where they overlap, there is a third supermassive black hole in the region that seems to be just caused by gas and dust coming together in these very special conditions. And maybe this is an explanation for how you got these supermassive black holes. This would be groundbreaking if this does pan out, because you would have a really interesting explanation. In this interview with Dr. van Dokkum, we talk about his discovery, as well as just how the field of cosmology is changing with these large telescopes. And I think you're going to really enjoy his answer to what he's obsessed with. So let's get on with this interview with Dr. Pieter van Dokkum. Pieter, one of the big questions that we have right now is, how did supermassive black holes get so big so early? And this sort of question about whether it was the supermassive black holes that came first or the galaxies around them. Are we any closer to an answer to this question?
Yeah, it is one of the most profound and vexing problems that we have in astrophysics, these giant black holes at the centers of galaxies. And there's no doubt that they're there. And we didn't expect them before they were observed. And we don't know how they got there, how they got this big, how they got to be where they are. We really don't know much about them at all. And they are, the most spectacular objects in the universe, I think, by some distance.
There was one that was just announced that maybe has 36 billion times the mass of the sun.
Yeah, it's unbelievable. I mean, the Milky Way has a relatively piddling one, but it's still 3 million times the mass of the sun. And so, they're gigantic, awe-inspiring objects. So there's two main pathways that people have come up with for growing these things. And the first is sort of tried and true, namely you explode a star, and then you have a core that's left that has nothing to hold it up against gravity, and then that collapses into a relatively small black hole of maybe 10 times the mass of the sun, or maybe 20 times the mass of the sun. So we know that happens in the universe. Those black holes have been seen in the Milky Way. They are, the remnants of stars that have died. And so one theory is that that's how these supermassive black holes started as well, by exploding stars, and then the remnants of those stars grew after that by accreting material, merging with each other. So you have a bunch of these little black holes that can then form a bigger black hole, and by accreting material, mostly gas, from their surroundings to get bigger and bigger. The thing is, it takes time to do that. As you can kind of imagine, if you start with 10 times the mass of the sun and you need to end up with 3 million or 3 billion, then you need to have a lot of growth over a long period of time. And so the alternative theory was, and has been proposed several decades ago, that perhaps you can start with a big cloud of gas that collapses under its own gravity, and then somehow that cloud of gas does not turn into stars, which is the normal thing that clouds of gas like to do in the Milky Way. But star formation is somehow suppressed, and that thing keeps collapsing and collapsing and collapsing, and forms a really big black hole right at the start of maybe 10,000 or maybe 100,000 times the mass of the sun. And then you have a head start. And so then it's much easier to get to 3 million, if you start with a much bigger number. And that process is not well understood at all. It's never been observed, maybe until now.
Right. Right. We'll get to that in a second.
Giving away the
Right.
punchline here. And anyway, that heavy seed model got a big boost with James Webb. Because one of the most striking early results of the James Webb Space Telescope is that that galaxies in the early universe, only 500 million years after the Big Bang, have black holes that are already quite big. And again, with that light seed model, where you start with an exploding star, it's kind of uncomfortably early to have 500 million years after the Big Bang already these big black holes. And so people have already suggested, like, well, maybe that heavy seed model where you form these black holes in what's called a direct collapse of a big gas cloud, maybe that has some merit. So that's the background. And then we found this new object that I think provides at least a partial answer to this question.
Right. Well, and we'll get to that in one more second. But if I understand, the challenge to this heavy seed model is that there are all kinds of feedback mechanisms that kick in as too much material attempts to come in. Like, we see a maximum size to our stars here because if too much material is flowing into a star, it heats up, the radiation pressure gets too high, and it limits the growth from that point forward. And so you only can get stars so big. And the same thing goes with black holes. And then we have the Eddington limit, which sort of defines how much material is able to flow into a black hole before, again, things heat up, gas ionizes, and anything else is prevented from falling in. So do any sort of heavy seed model require that those mechanisms are somehow shut off or avoided?
Well, there's two different aspects here, which are related, but they are separable. One is the initial collapse, so the first time that you form the black hole, and the second is after you form the black hole, the accretion of gas onto that black hole. And at that point, when the black hole is there, you do get these feedback effects of the gas that's swirling around the black hole will produce a lot of radiation, and that will indeed stop the flow of material coming in. But the idea in those heavy seed models is that everything happens extremely fast on a free fall time. And so the cloud collapses and collapses, forms maybe a few very massive clumps, black holes or proto-black holes, that then merge with each other and collapse into a black hole on a timescale that's much shorter than that feedback timescale.
But is there something that's allowing this to happen? Like, is there some process that's causing cooling for the gas that should be heated up, or is there some kind of turbulence that's driving material and allowing, breaking up the accretion disks so that it doesn't remain so hot? Like, does there need to be some additional mechanism that's going on?
Yeah, controversial, not clear. But there are simulations that have been done in the 2010s by Lucio Meyer and others, and also by Priya Natarajan here at Yale, mostly using analytical arguments, that suggests it's possible. The simulation results are particularly intriguing, where they looked at very high resolution what happens in a merger of two galaxies. So then the gas gets funneled to the center of the merger remnant, and there the densities are incredibly high, and there's a lot of what's called gravitational shear. That is, it's very difficult for small clumps to form and become self-gravitating because the environment is too turbulent. And so in that environment, the only things that can form and are stable against being ripped apart are big clumps. And then in the simulation, those big clumps started to become self-gravitating and kept collapsing until the very limit of the simulation. And so the suggestion was in those papers that if the conditions are extreme enough, so it won't happen in a regular cloud in the Milky Way where everything is kind of benign and you just form a whole bunch of stars. But if you get enough gas into a small enough volume with a large enough velocity so that you have this big shear and these very turbulent conditions, then maybe it's possible. And of course, the idea is that in the early universe, when these galaxies started forming, that those conditions might be prevalent. Where a galaxy first collapses, there's a huge amount of gas streaming towards the center. But preventing, getting rid of the angular momentum and getting rid of the star forming, tendency of gas clouds to form stars, those are the challenges in setting this up. I would say these heavy seed models are generally not favored by people. It was sort of forced in that corner by these heavy black holes. But I think if you did a poll, most people would believe that the light seed model is the dominant one.
And I guess, do you get a third explanation with primordial black holes?
Perhaps. I mean, yeah, you'd have to get the mass fluctuations, to create those things. So you'd need to set up a somewhat alternative cosmology to do that. But yeah, there are papers suggestions that do that. As far as I know, it's very difficult to test.
Right. But then you could walk out of the Big Bang with a black hole that already has a million times the mass of the sun, and then let it feed from there.
Yeah, I don't think it can be that high in those models. I think it's sort of small black holes, but it would give you another head start. That's absolutely true. So I think you still start with a relative. I don't know much about these models, but I think you start still with a relatively low mass seed, but it starts growing much earlier than.
Yeah. All right. Now the anticipation is maximum. Let's talk about your discovery, which is quite amazing.
Yeah. We bumped into this galaxy by looking at images taken with James Webb Space Telescope, literally looking, not analyzing catalogs, but just looking, which I can talk about, as well, like why one would do that. But we saw this strange object consisting of two rings, so slightly overlapping rings, each with a dot in the middle. So something that I'd never seen before and didn't think existed anywhere in the universe, a very unusual object. Then we were intrigued, obtained follow-up data with the Keck telescope, and later also follow-up data with James Webb Space Telescope in director's discretionary time, to try to understand what was going on. And one thing was pretty clear fairly quickly, and that is the way to form such an object is to have two galaxies, disk galaxies that are, have rotating disks like this, bump into each other more or less face on, so that the disks kind of hit each other like that. And then the other thing you need is a big bulge in both of these galaxies. So what happens then is these things collide, and the effect of the bulge on a big disk, if it falls straight through, is that you create a ring. The stars in the disk get herded into ring-like orbits. They're called collisional rings, and they've been observed many times in the local universe. If you have an impactor galaxy that hits a galaxy disk, right in the middle, close to the middle, then you get a ring forming. The beautiful ring galaxies that are known, and the idea is that here it happened with both galaxies. So the bulge of this galaxy hit this disk, created a ring. The bulge of this galaxy hit that one, created a ring, and so you get this symmetric situation where on the sky now you see two rings and two bulges in the middle, but the one impacted is the impactor on the other. And it turns out there's one other such object in the local universe, actually, which has been forgotten for 50 years. In 1976, Toomre and Lynds, or Lynds and Toomre, I should say, published an analysis, one of the first N-body simulations dynamical simulations of such a collision and the formation of rings based on a very similar object with two bulges and two rings. So I think people will now follow that one up because it deserves a bit of attention. Anyway, that part was pretty clear. And what was also pretty clear from Keck spectroscopy and from radio data from the VLA and particularly X-ray data from Chandra was that there is a supermassive black hole, active supermassive black hole in the system. It's very bright. It has very bright emission lines in the Keck spectrum, indicating a very high degree of ionization of gas. And the X-rays, come then from the region very close to the black hole, from the accretion disk. And the radio data probably largely from jets that are associated with the black hole. And so far so good. So we thought, okay, there's a big black hole in that system, probably in one of those two nuclei. That's what you kind of expect. There's a lot of gas being funneled into those nuclei in the collision, and they're very massive. We could measure that too. Each of the nuclei is the mass of a pretty big galaxy, so there's a lot of mass in that system. But then we looked at the positions of the X-ray data, the radio data, and of these emission lines in the Keck spectrum, and it turns out that they come from the middle, not from either of the nuclei. And what is going on is there's and further observation showed that there's a big gas cloud in the middle, ionized gas, right in between the two galaxies. And that in the middle of that gas cloud is a supermassive black hole that's actively accreting from the gas around it. And that is extremely unusual. To find a black hole that's not in the center of a galaxy, that's almost unprecedented. There are a few examples, but it's extremely rare.
And were you able to confirm that there are not supermassive black holes in the two galaxies that are colliding?
Well, in fact, we got this discretionary time on James Webb, so the director keeps a bit of time sort of separate from the regular proposals for discoveries that are made during the cycle, and so we applied for that, and we got the time, which was also really nice and unusual. And what that actually showed is that both of the nuclei also have a black hole.
Right.
Yeah. So that was an unexpected surprise. Each of the nuclei have an active black hole as well. Not as spectacular as the one in the middle, but more massive. The emission lines are very broad, indicating very high velocities in that region. So there's 3 black holes in the system. Each of the nuclei still has its own black hole, and then there's a black hole in the middle.
Right. And I guess that rules out then those two supermassive black holes finding each other, and maybe it was such a direct impact that they actually found each other really quickly and are beginning the merger process or already merged.
That would be very unlikely anyway, because then the galaxies themselves would merge as well. And so they clearly didn't. So they didn't pass like right through the center, and it's like there's these little nuggets in the very middle and so the chance that they would collide and the rest of the galaxy would sort of pass through each other is very small. But indeed, we know that they still have their original black holes, these two nuclei. And then the question, of course, was, where did that black hole come from there in the middle? What is it doing there? And there's a few options, and so we mostly 3 options, although you can always think of more. The first is that indeed it was ejected from one of the nuclei. Now that's unlikely because we see black holes in both, but it could be that one of the nuclei had 3 black holes from a previous merger, and then through a 3-body interaction, one could be thrown out. That is a possibility. That does happen sometimes, at least in theory. So that's an option. Another option is that it is a small galaxy, a separate galaxy that happened to pass in between those 2 nuclei, and that has a black hole that is very active. And so very unlikely to have a bright black hole associated with a very faint galaxy, but not impossible.
Right. So it's not necessarily directly associated with those other 2 galaxies. It's just perfectly lined up.
Right. Yeah. Passing through happens to be right in the middle. And the third option is that it actually was born there. So it was born out of that cloud of gas, and that the cloud of gas was created when the two galaxies collided. Because what happens is stars and dark matter is not collisional, so that will go through each other in a collision like that. But gas collides and it interacts and it gets compressed and it gets squeezed, and in that process, you can see it sort of being left behind. We see that famously in the bullet cluster, where you have this giant distribution of gas, whereas the two clusters have passed through one another. And so that is an option that then that gas is left over from the collision. And to test that, we got this follow-up data with James Webb, because in the first two scenarios, the velocity of the black hole is expected to be different from that of the gas, because the black hole is just passing through in those cases, if it was ejected or if it's a dwarf galaxy. Whereas if it was born from the gas, it should have the exact same velocity as the gas. It should be, within it, embedded within it. And interestingly enough, it is consistent with the velocity of the gas within 50 kilometers per second or so, which is very little in this context. So that provided strong evidence that it was born where we see it.
Right. And so then if you then bring it back to our original conversation, which of these mechanisms or combination of mechanisms do you think is at play to bring about this object?
Yeah. And so we think what we're witnessing is the birth of a black hole, of a giant black hole, that it was formed there very recently, and that it was formed in the collision of those two galaxies, that the gas conditions in that collision were so extreme, due to the compression of the gas and the gravitational shear preventing star formation, that a self-gravitating cloud formed and produced a supermassive black hole. So this would be the first time that we witnessed the birth of a supermassive black hole.
And so then would you be thinking, okay, it's conditions like this that get you supermassive black holes, or is this just that this is more recent in the universe? And so if you then think about the actual conditions of the very early universe, when everything was a lot denser, then you could have various conditions that were bringing together these supermassive black holes. Like I think, only two known objects in the entire observable universe that we've seen so far does not for all of the supermassive black holes make.
No,
right?
This kind of collision is going to be extremely rare. Right, you have to line up these disks perfectly, have them collide in a certain way, and they have to have a lot of gas to cause that compression. So I don't think many supermassive black holes formed in precisely this scenario. But what it gives us is a relatively recent analog that we can study in detail, and we could figure all of this out, of what might be happening in the early universe. And so it shows that if the gas has the right conditions, it's possible to form one of these black holes. And as we discussed in the beginning, that's not obvious a priori. Even if computer simulations seem to show it, the scales are so vast and there's so much physics at play with magnetic fields and outflows, and the scale of a black hole versus the scale of a gas cloud, to resolve all the scales, it's difficult. But seeing that it's possible, that makes a huge difference. It's a proof of concept that it is the heavy seed model, this alternative channel apparently exists.
Yeah, I think about this as an analogy. Like, we have no direct evidence of, say, the first generation of stars, but there have been discovered clouds of essentially primordial hydrogen and helium that are the same kinds of conditions, and we do see the equivalent of those first generation of stars start forming in those nebulae, and then you can use that as an analog to then think about what those conditions might be. So then if there was some kind of similar conditions early on, how would you try to uncover them? Is this like, I don't know, using the square kilometer array to search for hydrogen alpha emissions back in the dark ages, where, like, when would this, to get the number of supermassive black holes following the heavy seed model, when would this have been happening?
Right. Unknown. The frustrating thing is it might be just beyond what James Webb can do. Most models say it happens between redshift 15 and 20 or so. Kind of at the same time, more or less, as the population 3 first galaxies form. It's essentially when you have gas clouds of about 100,000 solar masses that begin to collapse, and then they either form a galaxy or a black hole. That is so. It's at roughly the same epoch, it may just be beyond what James Webb can see. But again, there's going to be regions of the universe where this happens later, a little bit later. And if it's at redshift 14, we should be able to see it, or 13. So it's conceivable that with Webb we'll get the first evidence of that. What Webb will certainly do is keep pushing back the boundary of galaxies and their black holes, and be able to measure the black hole masses that do exist, and continue this argument of working backwards in time, and to say how much time was there, at all in the universe, and how fast would the black hole have to grow. Those light seed models are really in trouble, potentially, or not. That we don't know yet, but I think that is the most likely pathway, and perhaps find more analogs like this one at later times. The more immediate thing, I think, is to study this object in more detail, and do simulations. Again, we know a lot about this particular object, and so doing in the computer, simulating the collision, simulating what happens to the gas, and seeing if you do indeed form a black hole, then we validated that particular simulation with this particular black hole, and then that can be applied to conditions in the early universe. I think that is a plausible path.
And obviously, to maybe find more of them, would that something like, say, Vera Rubin allow you to find more of these objects out there?
Yeah, I mean, we were unbelievably lucky to find this strange object in the Webb data. You can look for them in a variety of ways. One is to look for multiple active black holes. Like there are 3 in this system, if you find one in a spot where it shouldn't be, then that's a big hint, and then you can follow that up. And that's something that people are doing, or will be doing, with Rubin data. Exactly. It's been done with Sloan and with other surveys, with some success. You do find double quasars and things like that, but it's often hard to disentangle what's actually going on, whether it's just a merger happening or whether something new was formed. But that is one path, and another is with Euclid and Roman, we'll get high resolution images over huge areas of the sky. So crazy objects like this, with the double rings, if there are more that are like that have undergone such a collision, then we'll also find them.
Yeah, I know that Roman, Euclid, and Rubin together are going to find so many more gravitational lenses and interesting objects that people have never seen before.
It is truly a revolution. It's a bit different from Webb, where it's easier to explain, the huge advance, because we just see objects we've never seen before, and radiation at wavelengths that we had almost no knowledge of. And now we get more, over larger areas. But it's important to realize it's not just that you get more objects of things that you already knew, but also that you find objects that are very rare, but maybe rare because it's something that happens in a very short time scale, or that is exemplary of some process that's very common at another era, like this example. And so it's not the case that finding things that are rare is always kind of a niche, uninteresting pursuit. It could be the few objects that are really telling us what's going on.
I'd be interested to know how your perspective is shifting now that you've had a chance to work with Webb for 3-4 years now, and you're starting to, when you think about the models of the cosmos as you came into this process, and now you're seeing real practical examples of galaxies. And at the same time, I guess, sort of thinking about survivorship bias, like we see the bright things, we don't see the faint things. So we have to be very careful when we think about the bright things. But are you starting to kind of have a more nuanced take on early cosmology, or are certain hypotheses starting to feel more solid to you?
Well, I mean, the main concern, at least my main concern before Webb, was that it wouldn't see very much, frankly. There was a good chance that what happens in the first sort of billion years of cosmic history is little gas clouds forming little galaxies with a little bit of dust, and those are very blue, and were already glimpsed with Hubble, and it sort of the standard expectation was that that's how galaxies start. It takes a long time, and they first have blue and little, and then they grow, and then when you get to a few billion years, then you start to see big massive objects, and then sort of and quasars and things. That's where sort of the excitement is, and that epoch we studied already fairly well with Hubble and Keck and other telescopes, um, and it was completely different. The early universe is teeming with galaxies that just completely escaped Hubble's view. They are red, which is where Webb is optimized, and Hubble doesn't work that well. And they're bright. There's just the universe is incredibly complex and varied and populated. At these early epochs. It's you go back in fossil layers, right, to earlier and earlier epochs, and then you just find that at these early layers where you just expect very simple life, you see pretty well formed organisms already. That's what happened, and we didn't know that before. It was a huge gamble in a way, right, to build this telescope to explore the unknown. Luckily, we all knew it would find incredible things in many fields, exoplanets and nearby galaxies and star formation. So there was never a concern that it wouldn't be awesome, but that it was so awesome in this particular field of early cosmology. I don't think many people expected that. Hoped for maybe, but not expected. So that's the big story of Webb. That there's so much out there that we just didn't know about, and now we're trying to make sense of it. The overall story is things form earlier than we thought, and there's more stars around, more black holes around, more dust around, more gas around. Everything, the universe is more filled with exciting things at these very early epochs. So things started earlier than what we expected based on models and data that we had. How that all will shake out, I think, is still unclear. I don't think we've broken cosmology. I was part of the early paper, the early Nature paper, which said that there are all these early massive galaxies in the universe, which is still qualitatively true. But a lot of these objects turn out to have these black holes, and they boosted the brightness of what we were seeing, and so we attributed that all to stars, not to black hole light. And so now we're a bit more, moderate in what we think is going on, but qualitatively nothing has changed from that early paper. It's everything happens very early, and we don't know why.
That's great. I mean, these kinds of open vistas make this very exciting. Like, I think a lot of detractors think that astronomers are just like waiting for things to confirm their theories, but that's less interesting than things overturning your theories. That's far more fun and awesome, as you say.
Yeah, and in this field there isn't that much classic hypothesis testing. There's some, but the idea that there are these hypotheses out there, and then we try to falsify them. That is the way that science gets taught, and the scientific method, right? You try to falsify a hypothesis, you design an experiment. If you don't falsify it, the hypothesis survives. But that's not how we think. We think creatively. We think what could be out there. It's this spirit of exploration, and we're not trying to falsify anything. We're trying to discover. And so it's a very exciting phase, and it happens in astronomy fairly often. Interestingly enough, every time we open up a new regime of wavelengths or time or distance or whatever it is that we can explore, we find unexpected things. And that's been the one thing that's been constant. That we're always surprised with what we're finding.
Pieter, what are you obsessed with right now?
Oh, well, I'm always obsessed by the Oort cloud.
Oh, really?
Yeah. I really, really want to detect it in my career. Yeah.
I get this question all the time where people ask me, like, what will it take for us to be able to see the Oort cloud? And I'm always like, you've got to understand these objects can be one astronomical unit apart. They're objects 10 kilometers across or smaller. Yeah, there's trillions, but they're very far apart. So do you think that there's a practical way that we could start to map out the Oort cloud?
Well, I have some ideas.
Yeah.
Yeah, I have some ideas, but it's going to be very hard. I can tell you about one idea that failed because this is like people doing things they shouldn't. Namely, I had calculated how many Oort cloud objects at any given time would be in the ultra deep field image of Hubble in that little area of the sky, and then I was like, there's and then I calculated how bright they are, how bright this should be. Okay. So I did that, and it came to 30th magnitude, which is sort of the limit of what Hubble can see there. And then I was like, oh, you know what you can do? You can take all the individual images that were taken in that field, and then, correct for the orbits that Oort cloud objects should have, over the period that the Hubble ultra deep field was taken. Then you can shift them back and then add them up, correcting for all those orbits. And then you can do that for many different distances and blah, 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 blah. I spent months on this, got all the data, did the whole experiment and didn't see anything. I'm like, that's weird. And I explained this whole thing to someone, and they said, well, how bright are they? I thought they would be super faint. Like, it's okay. It's magnitude 30. And it's like, they were like, really? And it turned out that in my world of distant galaxies, you do distance squared to calculate how bright something is. Okay, and twice as far, it's 4 times as faint. In the solar system, it's reflected light from the sun, goes both directions. And so when something is twice as far away, it's 8 times. It's to the fourth, 16 times fainter, not 4 times fainter. And so they're actually magnitude 50. Way beyond what Hubble can see. So the whole thing was just a complete waste of time because I'm an extragalactic astronomer and I made an absolutely elementary error in the solar system. But I haven't given up. I have some other ideas.
Does it have to do with occultations?
No, I don't love occultations because then you can only do statistical detection, because it'll occult and then it's gone. And so it'll never occult a star again, that particular object. And I want to trace the whole thing. Yeah. I might as well tell you because I think it requires a 50-meter telescope, so it'll be a while before it can be done. I think you can do it with Orion in the background, the Orion Nebula. So the idea is you see it as a shadow moving across a background bright screen. So an Oort cloud object will, because then you don't have that problem that it gets so faint. You get the problem that it's very small, but that only goes as distance square, not as d to the fourth. And so I think you can trace it, kind of like I explained with the ultra deep field, against the bright glare of the Orion Nebula. Orion, because I think it is the brightest big area in the sky. The centers of some globular clusters are brighter, but those consist of individual stars, and the stars vary. That's no good. You need a smooth, background that doesn't change. And I think the center of Orion is the brightest.
And so, would you be looking to almost like track a spot in the sky and then like do a photometer on it so that you're just tracking the brightness of every pixel in your area, and then if something is like getting a little darker in a line,
that's right. So you shift it back again, all those images, so that they all line up. So you correct for all the possible lines that an object can go, and then you see if you see a little dark spot.
That'd be mind blowing.
It requires, I don't think it's even possible with James Webb, although I want to check those calculations because that would be really fun to look at Orion with James Webb for a long period of time. That alone would be fun.
Yeah.
But my rough calculation for a 10-kilometer object suggested that you need a 50-meter telescope, diffraction limited. which is a little difficult. But so I was thinking of writing a little paper just to explain the idea, and then let futures.
Maybe that'll create the gold rush for people to make a 50-meter telescope, or like bring back the overwhelmingly large telescope concept.
Yeah, that's right. 100. Yeah, that would
get a 100-meter telescope and put it on the moon.
Yeah.
Just so we can find that Oort cloud. Like, you want to find the Oort cloud. This is how we do it.
Right. But that would be really fun. And that's the main idea.
Yeah.
But
well, it would be. I really appreciate that, because now I can add that to my answer.
Oh yeah.
So when people ask me, how can we see the Oort cloud, I will include there are some interesting ideas out there on that. Yeah. But that's interesting. The 50th magnitude as a limit of what it would take to be able to observe one of these.
Yeah, it is. In reflected light is entirely impossible, because at that limit, the whole sky is covered by other things.
Yeah.
That's the problem. So you wouldn't be able to do it because the outskirts of galaxies begin to overlap, already, I think, at 40th magnitude. So, there's light everywhere.
Wonderful.
Yeah.
Well, I suspect that others in the audience will now be obsessed with what you're obsessed with as well. And so who knows? People may reach out for some collaborations. And
you know why I'm obsessed with the Oort cloud? I saw this comet. I forget the name, but it was about 15 years ago. It was a naked eye comet, really spectacular. And I was like, where did that come from? And I was like, I want to see the Oort cloud.
Yeah. Yeah.
I mean, until they get here.
I mean, I think it's weird. There's a whole generation of people now who have not experienced a bright, proper comet.
Yeah, that's true.
I think you're probably talking about McNeil, I think. But back there was like Hale-Bopp and Hyakutake.
Yeah, maybe it was 20 years ago. You're right.
Yeah, those are 25 years ago.
Oof.
Yeah, and they're mind-blowing. Like, you went outside and you saw this comet where you could see the central nucleus, and then the tail went up, and it was the most obvious thing in the sky.
Yeah.
And from this point on, we've just had these terrible little comets.
Yeah.
And the universe is really letting us down.
I agree. Yeah. And then it gets announced like, oh, naked eye comet, isn't it? And then I'm like, wait, where?
Yeah. We exactly. Oh, you mean when I use my binoculars and no, that is not a comet. And people have now become ruined. They don't know what a proper comet looks like.
That's right. No, everything's better in the olden days.
Yeah. Well, but then the people who lived through the 1966 comet just think even Hale-Bopp and Hyakutake are nothing compared to. So, and then every now and then, you think about ancient generations, people had things that got way closer and
think of
way
the dinosaurs,
brighter.
What they saw.
Yeah. Well, someone did a calculation that every now and then comets actually pass through the atmosphere. Can you imagine that? Like a comet going right through the atmosphere with its big tail. Like, that would be pretty mind-blowing as well. So there's a lot of stuff out there to see. Well, Pieter, thank you so much for taking the time to chat, and good luck with both your work in finding more evidence of direct collapse black holes and building the Mothra telescope. I really appreciate that, and we're going to do a lot of reporting and coverage. So get to work.
Yeah. No, thank you so much for your interest. Yeah.
All right. Thank you so much.
All right. Bye.
I hope you enjoyed this interview with Dr. Pieter van Dokkum. Now, as always, we have a larger interview with him, and this is about an observatory that he helped develop called the Dragonfly Observatory. And if that name doesn't sound familiar, I understand, but it's a really fascinating observatory that I've been pretty obsessed with for a while because it sort of ticks a lot of the boxes. It is made up of an array of dozens of consumer-grade telephoto lenses that are all attached together and then pointing at the same object. And you get this sort of mini interferometer where all of these lenses are all looking at the same object. It's incredibly fast, and yet has a very wide field of view, and has allowed astronomers to discover entirely new classes of galaxies. And Pieter and his team are working on a next generation that's going to do 1,100 of these lenses all stitched together in a new observatory down in Chile called Mothra, which is a more radioactive version of the Dragonfly. And so in the extra interview section over on Patreon, we talk all about those observatories and what's possible with this really innovative concept. I'll put a link in the show notes so you can go and check out that interview. It's completely free. There's no ads. content. I think you'll really enjoy that portion of the conversation. Now I'm going to give you some final thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Braley Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balock, Cy Nelson, David Gilton, and David Matz, Evan Pearl, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Monzo, Nick Borquez, Nick Solari, Paul Robach, Brent Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Cheplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I really am enjoying this time in astronomy with the new observatories that are all coming online. I think we got into this point where you had the Hubble Space Telescope and some ground-based telescopes, and people were very limited in the tools that they had access to and the questions that they could start to formulate. But now you've got all of those, plus James Webb, plus these new observatories, Euclid and Vera Rubin. Nancy Grace Roman is coming online soon, that there's just going to be so much survey data, so many interesting new objects that are going to start these kinds of conversations. And then you'll be able to have these ground and space-based telescopes that are coming online, the extremely large telescope, the Giant Magellan Telescope, that there's going to be so many ways to do follow-on observations of these interesting ideas, and it's just going to compound. And it's a really special time that we're now in astronomy, and I hope you will all be enjoying the ride as much as I do, both in having our questions answered and our new